These are the notes on an intro to concentration and molarity. We are focusing on solutions this unit, and so we're going to start to find ways we can describe concentrations of solutions. As a reminder of our solutions vocab, all of that is here for you on that first slide. We are going to see terms like solute and solution and concentration today and discuss those a little bit more. As a kind of reminder of what we have talked about and about concentration, concentration describes the amount of solute that is in a solution. So far, we've used terms like unsaturated, saturated, and supersaturated to describe how much of a solute can dissolve in a solvent. And we've looked at those numerically on the solubility curves. We've also kind of modeled what that looks like. These terms can describe the concentration of a solution, but they don't provide quantitative measures of a solution for us to analyze. And quantitative is talking about something numerical that we could then maybe analyze or do calculations with. These are a little bit more qualitative, just talking about the qualities. Same thing if we say something is dilute or concentrated. Dilute means something has a weak concentration, but it doesn't actually tell us what low amount of solute is present. Same thing with concentrated. It might have a strong concentration, but we don't know how much actual solute is in there. And so instead of using those terms like dilute or saturated, we have ways that we can quantitatively measure concentration. And those ways that we see in chemistry are measuring molarity, measuring molality. We could use percents, which is a part per 100, parts per million, which is ppm, which is parts per million, and ppb, which is parts per billion. The most useful way for chemists to measure concentration for a saturated solution, so something that has a decent amount of that solute in it, is to measure with molarity. And so this unit, we're going to focus on molarity. That's what we're going to talk about in the notes today. Later, we are going to talk about parts per million and parts per billion. Those are kind of the three that are going to apply to the concepts we are going to discuss. And this note at the bottom, we generally don't measure concentrations of supersaturated solutions because not all of that solute is dissolved into the solution. So if we still have some of those solids down at the bottom, not all of it's dissolved, and so measuring concentration wouldn't take into account the fact that some of that isn't actually dissolved. So what is molarity, if that's what we are going to use? So molarity, which we use a capital M as an abbreviation and as the unit, which is discussed down here, is the most common measure for the concentration of a solution in chemistry. It describes how concentrated or dilute a solution is in a numerical, giving us numerical value. And units, we measure molarity as molar. So you could have a 2 molar solution. We could also see 2M. And so we've seen that throughout this year so far. We haven't talked about it, but when we've looked at solutions, oftentimes you've been provided that molarity without us having talked about what it means. And that molar comes from us taking moles and dividing that by liters. And so that's what that unit is made up of. So how do we calculate molarity? Well, we take the moles of solute, what is being dissolved, over the liters of the full solution. Or we can abbreviate that with that molarity, capital M, equaling moles per liter. This is what is on your formula sheet. Under the solutions category are these two representations. If you like kind of this molarity triangle, you can take and make that into this triangle. If you would like, this one would kind of look opposite of that. We could say, okay, here's my triangle. That way, if I'm trying to find molarity, I would do moles divided by liters. If I'm trying to do moles, I would do molarity times liters because those are both in the bottom of the triangle. If I'm calculating for liters, I would do moles divided by molarity, because we make this the top of the triangle there. So if you want, write this down to reference, but both of these are provided on your formula sheet. So we need, calculating molarity requires those units of moles and liters. We see that in our formula, which means that if we don't have moles and liters as our units, we need to put those, or we need to get our measures into those units. So requiring moles and liters, we may need to do some conversions. So remembering from Unit 4 and stoichiometry, molar conversions, we know that the relationship between moles and mass is that 1 mole is the molar mass in grams for a chemical. And so if we don't already have moles for our solute, because it's easier in a lab for us to measure grams, we're going to need to use this conversion factor in order to do that conversion. So we've got just this as a little practice kind of warm up for us. So if we have converting 125 grams of aluminum fluoride to moles, well, aluminum fluoride is 1 aluminum and 3 fluorine. Aluminum has a molar mass, and I gave us a periodic table on the next page. That aluminum has a molar mass of 26.98, so let's round that to 27. So we have 1 aluminum, and then we have fluorine. Fluorine here has a molar mass of 19, and we have 3 of those. So that 19 times 3 is 57. We add those together, 84 grams is going to equal 1 mole for that aluminum fluoride. And so we can use that conversion factor to convert from grams to moles. So I've got 125 grams of that aluminum fluoride. I want to get rid of grams of my aluminum fluoride. I want moles. And then we can go ahead and put those values in. 1 mole is going to equal the 84 grams. So 1 mole on the top, 84 grams on the bottom. And then we can go through and do that calculation. 125 times 1 is 125, divided by 84 from the denominator, and we get 1.488, so I'm going to just say 1.49 moles of aluminum fluoride as my moles value. And once I have moles, that's a value I can put into that molarity formula. I provided this periodic table, which is available on Schoology for you, and then also the formula sheet is available on Schoology. We have our mole conversion from our molar quantities here. We might need to use metric conversions throughout this unit, and then our solutions formulas are down at the bottom. So we're focusing on that molarity today. We will come back to those other formulas in the next section of notes. So if we are doing conversions, it's our volumes that we will need to get to liters, because that molarity formula is moles over liters. Milliliters are the most useful unit of measure in a lab setting, just because we don't usually need full liters of something in order to see what is happening, because that's a lot of volume. But we need those units of liters to calculate molarity. So 1,000 milliliters is 1 liter. I have it flipped up here. 1 liter is 1,000 milliliters at the top. And so if we are in milliliters, we would need to convert to liters. If it asks for milliliters, you might also have to convert between those. So if we're looking at this 15.8 milliliters, just like with our conversion factors for our molar conversions, we set this up where 1 piece is going to go in the numerator, 1 is going to go in the denominator. I want to get rid of milliliters, so my milliliters is going to go in the denominator. So 1,000 milliliters in the denominator. I want liters, So 1 liter is going to go in the numerator. So we are doing that 15.8 times 1 divided by 1,000. And if you have done unit conversions in the past, dividing by 1,000, that's the same as us taking this decimal and moving it 1, 2, 3 to the left. So you could do that conversion that way as well instead of setting up the conversion factor. So we would have 0.0158 liters is equal to 15.8 milliliters. Going the other way, 2.47 liters to milliliters. Same setup, looking at that 1 liter is what we want to get rid of. So putting those liters in the denominator, 1 liter, and we want milliliters, so 1,000 milliliters in the numerator. So now we are multiplying 2.47 times 1,000, which means we're moving our decimal 3 to the right, 1, 2, 3, needing to add any zeros after, and to meet where our decimal would be, and then including our new units of milliliters on there. Again, your formula sheet has those conversion factors for easy access, so using that as you are completing problems will be helpful. So now let's go through calculating molarity. And as a reminder, that molarity is moles of solute divided by liters of solution. And so that is the formula we're going to need to be using. So white vinegar is 5% acetic acid. This is equivalent to a concentration of 0.83 molar. How many moles of acetic acid need to be dissolved in 5 liters of water to make this acetic acid solution? I like to go through and write out what my givens are, or even just what are all of my variables. We have molarity, we've got moles, we've got liters. So what of those things do I have? I have that 0.83 molar, so I'm going to use that. We have 5 liters of water, and so we're asking for how many moles. That's our question mark. How many moles will we have? As we look at this equation, I can go ahead and just plug in my pieces. I'm going to have my molarity, plugging that value in for that molarity. Moles, I don't know, so I'm going to plug in a question mark for my moles, or a variable x. And then liters I also have, so I can plug in that value. So we're going to have 0.83 equals, well, we don't know moles, so I'm going to just do an x as my variable, over 5. And then how can I solve this? Well, if I need to get that 5 away from x, the opposite of division is multiplication. So I'm going to multiply both sides by 5. And so x is going to equal 5 times 0.83, which is 4.15. And that needs a unit of moles. So 4.15 moles of acetic acid. Again, if you like the triangle, you can have that written down, that molarity equals moles per liter. With that one, we could see that we're finding moles, so we would have done molarity times liters. From that, the bottom of that is going to equal moles. Part B, how many grams of acetic acid would this be? Well, we have 4.15 moles. I know that in 1 mole of acetic acid, that's going to have a mass of whatever the molar mass is. And so I can find my grams of acetic acid. Let's find that molar mass. We've got that C2H4O2. Well, that means I've got 2 carbons. Carbon has a mass of 12, plus 4 hydrogens. Each hydrogen has a mass of 1. Plus 2 oxygens. Each oxygen has a mass of 16. And I get a molar mass of 60 grams per mole. And so plugging that 60 grams into my numerator, and now I can go through and do that calculation to find how many grams of that acetic acid would that be equal to. Going through now, 4.15 times 60 divided by 1, I get an answer of 249, and then I need my unit, grams of C2H4O2, grams of that acetic acid. Going on to the next example, if you are comfortable, you can always try this on your own. We can, again, remember our formula. So one 20-ounce bottle of Coca-Cola has 65 grams of sugar. We can see that right here on our ingredient label. Assuming all of those 65 grams are sucrose, which is table sugar, or C12H22O11, what is the molarity of sucrose in the Coca-Cola? So a 20-ounce bottle is going to be 591 milliliters. So this problem is asking us to find that molarity. Well, to find molarity, I'm going to need moles and liters. So molarity equals moles divided by liters. I'm going to have to look at what pieces I have here. I know that the volume is 591 milliliters. So my first step here is I'm going to go from those milliliters to liters. Let me do that conversion. 591 milliliters. And we can use our conversion factor from our periodic table. 1,000 milliliters are in 1 liter. So we're dividing by 1,000. I get 0.591 liters. And that I can plug into the denominator of that formula. So I found my liters by doing that conversion. Now I need to find moles. Well, what information do I have? Well, I know that I have 65 grams of sucrose and I have that molar mass of sucrose. So I'm going to now try to find I need to go from my grams to moles for sugar. So let's use the information that we have. We are given 65 grams of C12H22O11, and I know that 1 mole equals molar mass. So if I can find how many grams of sucrose are in 1 mole, I will be able to do that conversion. So finding the molar mass of that sucrose, so C12H22O11, I've got 12 carbons. Each carbon has a mass of 12. I've got 22 hydrogens, each has a mass of 1. And I've got 11 oxygens, each has a mass of 16. And I get 342 grams per mole is the molar mass of sucrose. So let's put 342 in the denominator there. And I'm going to get rid of my formula down here because I already have it written down. So we've got 65 times 1 divided by 342. That's going to be 0.19 grams of, moles of our sucrose. A typo up here, get rid of that grams. And so now we have that. That is our mole conversion. So we can put that in for our moles up top. So 0.19 moles of sucrose divided by 0.591 liters. This is going to be a concentration of 0.32 And that unit on our concentration is molar. Molar, that's our concentration of sugar in Coca-Cola. All right, feel free to try this example on your own or do it with me. Example 6, fluoride is a useful component in toothpaste because it strengthens tooth enamel. However, if too much fluoride is present in the human body, it can be toxic. In the western United States, drinking water has a sodium fluoride concentration of 3.58 times 10 to the negative fifth molar. How many liters of drinking water would a human need to consume in order to ingest 0.05 moles of sodium fluoride? So as I'm looking at this, I have that molarity unit. So 3.58 times 10 to the negative fifth molar. And then thinking back to our formula up here, we've got that moles of molarity is moles divided by liters. So I'm going to just write my formula down. So moles, the problem is asking if we are ingesting that many moles, how many liters would that be? And so as we're looking at this one, if you like the triangle, you can consider that molarity is moles over liters. So if we are trying to find liters, we would do moles divided by molarity, or you can set this up and use your algebra skills in order to isolate your unknown. I'm going to go through and do this using my triangle. So liters are going to be moles divided by molarity, and I've given 0.05 moles, dividing that by 3.58 times 10 to the negative fifth molar. That's a really low concentration, and so that's why it has that scientific notation. And then going through and plugging that into my calculator. So we got 1396.6. I'm going to stop there. So you would need to consume 1,396.6 liters of that drinking water in order to reach that limit. So by consuming that, some of it's going to pass through your body, and so it's not all going to compile up, and so that is why it is safe to have that fluoride in our drinking water. Reach out to your teacher with any questions. There is a molarity worksheet and a molarity check-in. There is no pivot or lab until after we discuss our next topic.